And this is really the last thing of importance in chapter 4 before we move into chapter 5. You've had inductance before in physics, and you understand the basic concepts. So I'm just going to recap what we did last time. I said that 1/2 Li squared. In general, the lumped element symbol for an inductor is just that. But it could, that represents any possible scheme of wires, usually that are really wound around something, that where magnetic energy is going to be created by current flowing in there, and that magnetic energy is likened to, and that energy can capture the value of the self-inductance, which is L. 1/2 Li squared is equal to 1/2 times the integral of mu times h squared over the volume. And we did that last time. So we could always find L by simply saying 1 over I squared times the integral of mu times magnitude of h squared over the volume. And I did a couple of, that's over the entire volume, where magnetic field exists created by that current I. So usually with the problems, this is one method. It's the magnetic energy method of calculating the inductance. Do you remember what I said about the inductance in general? There's an internal inductance, right, inside the wire, and then there's an external. And the external is very hard to calculate unless you know the closed path for current. So they have a formula for partial inductance in the book. That's it's sort of a coarse estimate of the magnetic energy, of the inductance outside the wire. Does everybody recall that, class? Right. I give you homework, right? It did appear.
Like quantum problem.
Just one with magnetic energy, right? I thought it was. No? Duncan was.
It might have been.
Did anybody do
It
it?
was find the inductance of a wire length L.
Right, and that's using the partial inductance formula.
Yeah.
Yeah. All right, so anyway, I gave you a problem with partial inductance, and this is the general formula. I know you've got your test back, so it's probably more on your mind just looking at your test, but that's how you get with the actual energy thing. By the way, when we talked about internal inductance, of a wire, let's assume this is going to be infinitely long, so let L go to infinity. And we talk about the internal inductance per meter. So let L let the length be 1 meter and the radius A. Do y'all remember what the internal inductance is per meter for wire? We did this one. Anybody? There's one fact about this that's very, very important. I got a wire of radius A, and I want the inductance per meter. Does anybody remember what it was?
I over 8 pi.
Not I. I is not, inductance is never a function of current. You're close. It's mu 0, right? Or it's mu actually, over 8 pi. And what was, and that's henries per meter. What was so important about that or unusual or unexpected?
It doesn't have A in it.
Has nothing to do with the radius. The internal inductance of a wire is independent of radius. It's only a function of mu, which is the permeability of the material, and it's divided by 8 pi. That's real important. Now the external inductance is something that you can actually estimate using the partial inductance formula. But this is rather an interesting find. Now we're going to talk about inductance using something called flux. And this is the one that you'll see Dr. Gross, if you have him, using a lot. And a lot of people prefer this. And this will allow us to get both self-inductance. Self-inductance is the inductance associated with the current creating magnetic energy within the area where the current, or within the realm where the actual conductor is. Then there's mutual inductance, and that has to be, that's associated with the amount of flux actually that penetrates a secondary circuit. So I'm going to talk about mutual inductance now. All right, mutual inductance, there's symbols like L sub M or just M. The units are still henries. All right, all inductance has the units of henries. So how do you get mutual inductance? First, we talk about the concept of magnetic flux. Magnetic flux is usually symbolized either with phi or with psi, depends on what book you're looking at and even where in the book you're looking in some cases. And flux is the integral of B dot ds over a surface. Now, if B is in Webers per meter squared, if we integrate that over a surface, we get Webers. And Webers is the usual common term, the symbol is Webers, for magnetic flux. Now here's the thing. Either self or mutual inductance can be gotten from this concept. So if we have, and I'm going to show you how this works because this is where it really makes sense. If we have a current I, or we assume a current I, let's assume it's an infinitely long wire for starters, and we'll put it on the z-axis. And then I come out a distance A, and now this is the classic problem. I'm going to have a second wire, and it's going to have a width W and a height H. And I want to find the associated mutual inductance between this current conducting system, which is an infinite line, and this loop. By the way, this has a very real application. If you think about very long power lines and you put a loop next to them, this is what this is related to. Actually, I'll finish the story in a bit. So what I want to do is find the mutual inductance between these two. Here's the steps. First, I find the B field. And what is the B field? If that's Z, let's call this X and call this direction Y. So what would B from the first system be here? I want the B field here. Well, this dimension is Y, correct? What's the B field always? It's mu always, right? There's always mu, and then it's times H, correct, class? What's H from an infinitely long current carrier? Just had a test. Anyone? It's I over 2 pi rho. And it would be, in this case, the minus AX direction. Do you all remember this? Now, try to see the similarities between electrostatics and magnetostatics. I'm just going to put this here. What is the E field from an infinitely long current? Infinitely long charge wire with rho L per meter.
Q over 2 pi?
It's rho L, well, yeah, over 2 pi epsilon naught, or epsilon, right, times in rho, right? But here, my rho really would be Y, wouldn't it, class? Because I'm measuring Y, and here, this would be Y too, and it would be in the minus AX direction. But look at the similarities. Both proportional to the distance away, inversely proportional to the distance away. The constant is 2 pi, right? For the E field, epsilon is downstairs. For B, mu is upstairs. But there's a lot of similarities here. All right, that's the first thing. The second thing you do is you find the amount of magnetic flux that penetrates the actual surface where the wire or the secondary circuit is the perimeter. Follow me? It has to be all the B field dot ds that penetrates or that is captured within this. So now I take the integral of B dot ds, and therefore it's the integral of that, which is mu I over 2 pi y minus ax, and dotted ds. I'm going to ask the class this. What would ds be for this right here? If that's z, that's x, and that's y. Anyone?
dy.
Say it again.
Dx, dy.
Right? Not dx, dz, dy, right? dz, dy, in what direction? Oh, you're right.
C direction.
Ax, right? It's got to be perpendicular. Ax. And so that would be ds, which would be dz, dy, ax. Now, about the limits. This is the magnetic flux. Well, for dz, where does it go from? Well, it goes from any point to any point plus h, right? So why don't we make any point 0, from 0 to h? So z goes from 0 to h. What about y from?
Even W.
From a, right, to a plus w, right? You all see this, class? Because I call that the y direction. Everybody agree with me here? Okay? Guys, you ready? You have a test next period? I see you making a sheet there. Okay, I'm not going to bug you. I'm glad you came to class. Are you with me there? What happens for this? That flux would begin mu I over 2 pi, right? Now when we integrate dz, we just get h, don't we, class? What about when we integrate, we know ax dot ax is 1, we get a minus sign. That won't matter in a second. We integrate 1 over y dy, we get natural log of y from from a to a plus w. A plus w over a. Now that's the second thing, so we've got the magnetic flux. Third, we find inductance. The mutual inductance, either this symbol or L sub m, either one's appropriate, is simply the magnetic flux created by the first conducting system that penetrates or is within the second conducting system. And here, and then we divide it by I. So if we take the flux created in the secondary circuit and we divide it by the current, we get the mutual inductance. And therefore, if we take a look at this, we get minus mu h over 2 pi times the natural log of a plus w over a. And here is something I'm going to tell you. Mutual inductance or self-inductance is never negative. Make it positive. The way we deal with the concept of negative or positive has to do with the dot convention that you've probably seen on transformers. Has everybody seen this with transformers? That there are dot, how many have? You're familiar with it? What class did you see it in?
I saw it.
All right, well, the dot convention really is something that we're going to cover a little bit later, and that comes in chapter 5, but we never talk about negative inductance. That's kind of a misnomer, because inductance really has to do with energy. You can't have negative energy. I always got to catch myself on this one. Physicists have a way of creating these non-existent concepts that are allowable just so they can solve problems, but there is no such thing as negative energy. It's sort of like, I don't know, when I hear of negative mass, that actually does exist. They're called holes, but it doesn't really exist. It's just a created concept to solve physical problems. You know what a hole is, everybody? Remember holes and electrons in semiconductors? Well, holes have a negative mass. Why? It's an absence of electron. So it's got to have a negative mass. It's interesting thoughts, and it's only used to solve problems that doesn't really exist. So that's mutual inductance for that system. Now, here's the question. I showed one turn there, right? What do you think happens if instead of that, I break this like that, and then I put a second turn around here, right on top of the other one? Say it's shellac wire. What do you think happens to that inductance? Just think about it. Yeah, as a matter of fact, what happens is really the area doubles, doesn't it, class? You could say that the area doubles. In fact, the inductance in general, no matter how many turns you have, if you have n turns, this inductance will just be multiplied by n. And that's as easy as it gets. Are you with me? So, in this case, if we just have loops of wire, say it's shellacked wire, thin wire wrapped right on top, the flux keeps going up by n, the number of turns. Now here's the thing I wanted to tell you. It's kind of an interesting story. This really has to do with something called transformers that we get into a little bit later in the next chapter. But you see, what can happen here is your mutual inductance has to do with the amount of really power that you can pull out from one system to the other. Transformers use the concept of mutual inductance. And long ago, I don't know how long ago, the power company used to stretch their power lines all through farms out in the Midwest and in the far West. And they'd go for hundreds of miles, right? So some farmer had some interest in getting free power, went up there and he had a coil of wire that he created that was very close to a power line that pulled a lot of current. And off of that, he had a step-down transformer, and then he used that power for free. Well, the power company is very aware of power losses. They're going to get some loss. If they have a power line over the ground, it induces eddy currents, it's a loss. But they're getting a lot of loss in this area. And they went through and tried to figure it out. He hid this thing in a tree, by the way, as I recall. And he had it well hidden. So they're trying to figure out how are they losing all this power from this point to this point. Finally, I don't know if you know this, but like the power company, when it has eminent domain, it can run lines, it can do stuff like this, and they can also go on your property anytime without announcing it to you and do maintenance stuff. So finally somebody noticed this strange box up there that's even almost hidden. And they found out it was in fact a transformer. It wasn't touching the wire, but it was close enough to extract power. And there's a lot of violations in this one. Anyway, that guy got in a lot of trouble. But I'm just going to tell you, that's the type of transformer that he used, that I'm showing you right there. It wasn't something that even break into the line. All right, that's mutual for that system. Now we're going to take a look at mutual at a couple different systems. And if I have time, when we get to chapter 5, I'd like to build a coil gun and just fool around with that, yes. All right, now we talk about some examples of how to calculate inductance for given systems. First one I'm going to do is a toroid. This is a good one. I want you to be careful on this one. We're going to assume that we have a core, and let the core have a permeability mu. All right. And I'm going to say that it has a radius of A. We usually call that the mean radius. And this wire has a radius of R wire here. R core, R sub C. So this is the system. And now I'm going to do this. I'm going to put a whole bunch of turns. Follow me, just continue, wrap turns, and finally, and I want to know what the actual inductance is, the inductance of that system. So here's the thing you have to realize. I wanted to wrap them all the way around, but I'm going to assume all the magnetic flux created is contained within the core. Right? Can everybody understand that, class? Really, I should wrap this all the way around. If you want to, you can, but you get the idea, right? I got a wire that's wrapped around, and I have N turns. Now, with that N turns, to calculate the inductance, the first thing I do is assume I have a current I flowing in each one of those turns. So imagine that. Think about this. Just think of a very thin donut, right? And then wrap coil around that donut. Can you all imagine that? We're going to also assume one thing. We're going to assume that A is much greater than R core. So the first step is to find the B field or H field inside of here. So I'm looking for B or H inside that core. Now, remember when we did this last time, I told you the way to think about it is just cut the thing right in half, right? If you cut it in half, it looks like this. You have the mean radius is A, and you have this, and then you have a whole bunch of turns here. This is cutting it right in half. If they go all the way around. And I have N conductors, or N turns, and each one of those turns has a current I going into it. So each one of these things has a current I into the board, right? And then I said, I'm looking for the H field or B field. Well, I know that I can use the integral of H dot dl over the closed loop is equal to the integral of really I, or really J dot ds, or I could just say the I enclosed. Now pay attention to this because people mess this up. Well, from the right-hand rule, and this is something we did last time, I know that if my fingers curl around in the direction of the current in these tightly wound turns, my thumb on my right hand points in the direction of the H field. The H field is going to be right around here. It's going to be azimuthal, right? And it'd be in the minus, it won't matter the direction, but it's going to be going this way if the current's going into the board. Do y'all see that? All right. So this is going to be 2 pi, right, times A, since A is the mean radius. And I'm going to assume that A is so much greater than RC. The distance between here and here and here and here is insignificant. So it's 2 pi A times H phi is equal to the current enclosed. But how much current is enclosed in this is my Amperian path. Can you all see it? How much? It's not I, what is it? N times I, right? Because I have N turns. So it's going to be Ni. And that means H phi would be equal to N times I over 2 pi A. It would be in the A phi direction, but it won't matter. And that means B would be equal to mu H, or it would be equal to mu times N times I over 2 pi A phi direction. Now I have my B field. All right. Now please watch this next one. Now I need to find the amount of flux. If we take a look at this cross section right here, it looks like this. All right? This is our core. And what I want to do is find the amount of flux that penetrates one turn. You all follow me on this? Right? Just one turn, not N turns. That's the amount of flux. I mean, that's the B field that's flowing here, right? The flux through one turn that would be equal to this, and it would be equal to the integral of B dot ds. Correct, class? Now here's my contention. You see the B field is circulating like this? And ds here would have a normal component in parallel to the actual B field, right? If I integrate B dot ds, really, I'm just taking the area here because I'm assuming the B field here is the same as the B field here. I'm taking this area and multiplying it by the B field. So I can approximate this thing as simply equal to that B field, right? In magnitude times the area, cross-sectional area. And that means my magnetic flux is simply equal to mu I, right, N over 2 pi A, that's the B field, times the actual area, which is going to be pi A squared. Does everybody see that? And that's the flux that's penetrating one turn. Okay.
Wouldn't that be pi RC squared?
For RC squared, pardon me, you're right. RC squared, thank you. RC squared, you're absolutely right. It's the radius of the core for that area. Now that's through one turn, right? But we need the flux penetrating all turns, don't we, to get the self-inductance, or in this case, itself. So now I can say, and they use this symbol. This is called flux linkage. This is the symbol for flux linkage, and it really is equal to N times the flux penetrating one loop. So that means when I take n times this, now I get mu I n squared over 2 pi a times pi RC squared. Do y'all agree with me there? And now we can get the inductance. Now we can simply get the inductance L, and this would be a self-inductance, would be equal to the flux linking all those terms divided by the current causing them. And that means it's simply equal to mu n squared over 2 pi a times pi RC squared. And the critical thing here is just knowing the area, the perpendicular area here. Because if this was elliptical, it really wouldn't change things as long as the radius, the largest radius of the ellipse was still much, much less than the radius A out here. It won't matter, but you have to know the area. And that's generally, that's the inductance of a toroid. And we wind these things, actually, we do this for a lot of reasons. For filtering purposes, we do this and we make something else called a common mode filter that I'll show you later. But that's the actual self-inductance of this. Another common thing that they try to get is the self-inductance of remember how I contrasted the toroid to the solenoid in the formulas? We're so similar. Y'all remember that? Well, I'm going to leave the toroid out there, and I'm going to make a comment or two. And then we're going to do the solenoid. If you look over here, if I look at this LS, right? It's mu n squared, but what is 2 pi a really? That's the perimeter, right? It's the length, isn't it, class? It's the total length if we cut that in half. So if we divide this by something I'm going to just assume is length, it's the total length of that solenoid. That would be there. And what is pi RC squared? It is the area, right? So A. Now box what I'm showing you here. The L is something, if anytime you have a lot of coils of wire over a core, and you know the cross-sectional area, it's got to be a lot of coils of wire, and it's got to be something where the length of the actual of the system has to be much longer than the radius A. Right? But if that is the case, this formula will always work. And for a toroid, where we just have a very long piece of, I'm saying very long, a piece of core material, core mu, and we wrap turns around this thing. And I'm going to say I have n turns, and call this thing L, length. Now, you remember we created a formula way back in the day. We figured out the H field and then the B field from a single turn, and then we integrated a differential amount of current in one turn over the actual length. Do you all remember that? Some time ago. But we found dead center here in the center, we could say that the H field was equal to mu I times N divided by L. I don't know if you remember that, or that's not, this is actually it. It's Ni divided by L. Does anybody remember that? We did this thing some time ago, but this is for something where, let me just say this. If this is RC, if L is much, much greater than RC, like 100 to 1, then what I'm showing you works. That is going to be the B field dead center. And the B field will not be a function, hardly at all, of the actual radial distance from the center. It'll be about the same everywhere. It's very interesting. As a matter of fact, along the axis, it's about the same until you get very close to the ends. So if that's the H field, I can say the B field. As a matter of fact, if we give this a direction, call it Z, this would be in the AZ direction. I can say B here would be equal to mu H, would be equal to mu I over times N over L AZ. Now that's the B field right here. Now what I want to do is find the amount of flux through one turn. And again, the area looks like this. This is RC. And therefore the area is pi RC squared. So the flux through one turn would be equal to the integral of B dot ds, right? That's the B field. Mu I over 2 pi, I'm sorry, mu I over, mu I n over L AX, and ds would be really, you could say it's rho d phi d rho in the AZ direction, but it really, at this point, is immaterial because we just want to find the area there. And you could put it as a double integral and say from rho goes from 0 to RC, I'm sorry, phi goes from 0 to 2 pi and rho goes from 0 to RC. But really what we're going to do is just take this B field magnitude and multiply it by A, because the B field is not a function of the position here. So that means it's going to be mu I n over L times area, which is just pi RC squared. And that would be the magnetic flux penetrating one loop. Does everybody see this, class? Guys, with me? Do you see it? All right, I gotta make sure everybody does. Right, it's just the B field times the area. Now, if that's the magnetic flux through one turn, what would the flux linkage be through all turns? This is for one turn, right? It's one turn. How much flux through all turns?
Mu I n squared.
Just n times that, right? It's going to be n, that's what I'm looking for, n times the flux in one turn, correct? So that means this becomes, you were ahead of me, Duncan. You try and do the, you're giving me the answer. This answer, pi RC squared, right? And then if I wanted the inductance, what do I do? That's right, just divide by I. And dividing by I does this, and that would be the inductance of the solenoid. Now, if you look here, you'll notice what happens. Here, we get, same as there, we get mu n squared comes out in front, and then we see it's proportional to area, inversely proportional to length. And that's the inductance. And I have a comment here. You all see this? So, if I have a system where, suppose I have a solenoid and I bend it like this, and I got all these wires, right? So I got all these turns, N turns. The only thing I need to calculate the inductance, assuming that this core length, I mean the length here, is much greater than the actual radius here. If that's the case, and there's a lot of turns, then I can say that inductance is still going to be mu n squared, however many turns I have, times the cross-sectional area that it's penetrating, and just divided by the perimeter length, divided by really the mean length through here, that would be L. Can you all see that? And that's a handy thing to know. So you don't get hung up with, you know, oh, well, it's bent like this. It's bent like a snake. Don't worry about that. That's the total length, whatever that is, and use it. It's going to be just mu n squared times the cross-sectional area divided by that total length, and that's it. And you don't have to worry if it looks like a snake or whatever. And those are things that happen in the real world because they have toroids and stuff like this, that to fit them in, they have to bend them and stuff like this, fit them in boxes. Okay. So that's another one. I'm going to do one more, and this is going to be mutual inductance. And I'll give you problems where you'll do self and mutual. As a matter of fact, we may do one other one too. Because the more problems you see done using this concept of flux linkage, the easier it gets. And the more clear it becomes. contrast this stuff. How did we find capacitance or resistance for any system? What did we do? We had to assume something, right? For resistance, we usually assume current, right? Then from current, we got J, right? And after J, we got E. And then we integrated E dot dl to get V, and then we took V over I to get R, right? There was an assumption. First thing is assume current. If we wanted capacitance, we usually assume charge. Then we got the D field, then we got the E field. Then we integrated, right, E dot dl between the plates to get V, and then we said that capacitance was equal to Q over V, right? So we assume charge now. Here, if we want inductance, we assume current. And then, after we assume current, we find H and then B, and then we find the magnetic flux through whatever system, if it's mutual inductance through the secondary system, if it's self-inductance through the actual, the primary system, but only in one turn. And then to find the total inductance, we take the flux penetrating one turn times the number of turns, and we divide it by I. Inductance is never a function of I, and neither is resistance, unless they're nonlinear. We're not there yet. And and capacitance is never a function of voltage or charge. Remember that. They're always only functions of the geometry and materials. That's important. Okay. I'm gonna do one more. Yeah, let's do this one. This one's one that I think helps shine a light on some things that get a little confusing. All right, this is going to be 2 wires. So draw 2 infinitely long wires, right? Both of them are going to have a radius, I'll call it just RC. So I got 2 wires, identical, same radius RC, and they're separated from the center to center, separation distance of W. And what I want to do is get the inductance of these things per meter. Now, here's the assumption here. You got to understand this. We're assuming that this works in a differential mode. In other words, current flows this way and current flows this way, same current. Think of an extension cord plugged into a wall, right? Current comes down one wire and goes back through the other wire, right? It's called a differential current. If they were in the same direction, that's called a common mode current, right? But this is differential, and this is the way typically most extension cords and systems are used. Power lines have this, all right? They have current going down one line, coming back through another. All right, now if I want the inductance per meter, so I'm gonna say the length here is gonna be 1 meter, and I'm looking for the inductance per meter of this system. I've just showed you the currents. These are currents I've assumed because I'm trying to calculate this inductance. So we start out by saying, well, what is the B field here at any given point? Let me take this as my z-axis, right? So if I want to know at this point from this system, now listen carefully, this is a good problem. If I want to know what the B field is here, if it's infinitely long, or H field, if I'm a distance, this is the center, and if I'm out a distance, say, rho, to this point, and I wanted to know the B field. Well, what would it be? Or B field or H? Let me go B right away. We know it's mu times H, right? What's H for an infinitely long current? I proportional to I, inversely proportional to 2 pi rho, right? In the A phi direction. You all with me on this, guys? Right, this is an infinitely long current. We're outside where the current exists, so that's the B field. Do you agree? It's just mu H, right? Now I have that, that's my first step. Now the second step is, now I need to get the flux. I need to get the magnetic flux per turn. Here the concept of turn kind of loses its meaning because the turns close at infinity. This is one big turn, if you can imagine that. Follow me on that, class? So you don't have to worry about turns in the true sense. We only got one. And it closes at infinity. But the magnetic flux would be the integral of B dot ds. And that would be a double integral. The B field is given by this. It's mu I over 2 pi rho in the A phi direction. But now I need ds here. Now I'm using cylindrical symmetry, so what would a differential surface be here? Well, how about this way? What's the differential? D rho. It's d rho. What about vertically? D z. And what direction is it in? A phi. Don't worry if the negative sign pops out, ignore it, because we know this is going to be strict positive. So this is going to be it's going to be d rho dz a phi. Now, this is important. This is where people mess this problem up. Where does rho go from? I'm going to make a comment here. We don't care about the internal inductance per meter of the wires. We know that. This one is mu 0 over 8 pi, right? This is mu 0 over 8 pi. We're going to add that in at the end, per meter. Right, we're going to get there. But we only care about the inductance associated with the magnetic flux between here and here. So where do we start the integral at? Not 0. Think of that wire, RC, right? We don't start at 0 because remember, that would require that's the energy inside or flux inside the wire. You see that? We're just worried about the flux outside. So here it would be from RC to where? Take a look. To, right?
W minus 2RC.
And it would be, that's exactly right. It would be W minus 2RC, exactly right. To W minus 2RC. And what about DZ? Where does it go from? Since it's per meter. How about 0 to 1? Right. It's going to be per meter. Y'all agree with that? All right, what is this going to end up being? Well, that's going to be equal, A phi dot A phi is 1. I got a mu, I got an I got a 2 pi. I integrate 1 over rho d rho and I get 1 over rho integrated is natural log, and I have to evaluate it from here to here, so I have the natural log of W minus 2RC over RC. And then I integrate dz from 0 to 1, or I get 1. So that's the magnetic flux between RC and W minus 2RC, right? So now I take that, and I'm going to say there's only one turn, so I don't have to worry about multiplying that by n. And now I divide that by I, and that is my inductance. And that's the self-inductance of this system, but it's external. And write this down, that's external. The total inductance, total L per meter, is equal to 2 times the internal inductances of those wires, which is going to be mu over 8 pi, plus this, which is mu over 2 pi times natural log of W minus 2RC over RC. And I'm going to show you something to contrast magnitude right now. For now, let's assume mu is just mu naught, all right? So I want you to take a look at this for a second. I'm going to factor out the mu naught. Let's see. I'm going to go ahead and factor out mu naught, and I'm going to factor out 2 pi. And then I'm going to be left with, well, actually, this is going to be 4, this is going to be 1/4 here. Yeah, 2 pi. And so I have really 2 plus, and that's going to be natural log of W minus 2RC over RC. Now, I want you to take a look at this with me. Typically, W is going to be of the order of 1,000 times RC. If you think about just a standard, well, I'm going to say for our system, it's that. And then I'm going to explain something. If you think about 2 wires typically strung where you have a differential current like that, power lines, for instance. If you have one power line positive phase, let's say an A phase, then the B phase over here, there's usually a fair distance of the order of tens of meters between them. But the radius of that wire is maybe centimeters. Follow me? So this is at least something, it's probably much greater than that. So what happens to the magnitudes of this? This is 2, it's proportional to the internal inductance, right? What happens when we take the natural log of, say, 1,000 RC? We really get the log of about what? 1,000 here, right? Really, it's about 1,000. What's the natural log of 1,000? Anyone on your calculator? The log is 3. What is the natural log?
You have mu naught 4 pi factoring to 2 times mu naught over 2 pi. Should
Sorry.
that be 1/2?
This is a half. My bad. You're absolutely right. This is a half. My bad. Thank you, Duncan. You're absolutely right. But what is this? Natural log of 1,000 is?
6.9.
My point is this. The actual external inductance is much, much greater than the internal. Even for typically like power lines that are separated a great distance. But if you're talking about twisted pair circuits, you know what a twisted pair is? You have wires that are twisted with each other and they have a fast twist rate, like Cat5 cable has this, a lot of things. Because the separation distance is so small, they have a dielectric insulator, then all of a sudden the internal inductance takes precedent. Then the internal inductance will dominate. And that's the thing. If the wires are literally next to each other and wrapped tightly in order to prevent EMI and EMC problems, then those, in that case, the internal inductance per meter takes precedence, which is 2 times mu over 8 pi, right, per meter. And if they're separated by a great distance, the external inductance, or this term right here, takes precedence. That's important. Okay. The final example I want to give before we move out of here, and I'll give you a bunch of problems. And this is a very typical kind of question that you get on any kind of tests on magnetics. It wouldn't matter if it's in physics or in engineering. I think this is fairly common in both. Physics would have more fundamental. They'll come up with a strange shape of a wire and they want the inductance, but engineering is more applications oriented. So if I have a long, very long core material here, a rod, and say the thing has radius RC, and it has a permeability mu, and let's just say mu is much, much greater than mu naught. And then I have here, I'm going to wrap a bunch of turns, and I'm going to go ahead and say I have some sort of a voltage here, V, but it's going to generate a current I. Now, what I'm doing is showing you how to calculate the mutual inductance between a core wrapped with 2 different turns ratios. So this is going to have N1 turns. Now I'm going to say there's another coil down here. This would be like a secondary. And this has N2 turns. I'm showing you them straight, but I'm going to tell you the way a real transformer works is this thing would be a big toroid type thing, all right? There wouldn't be any end here and any end here, but I'm going to use this method, okay? I want to show it to you straight. Everybody with me on this? This does work, by the way, what I'm showing you. So if I have a current I here, we're going to assume that all the flux penetrates this. We're going to assume it's long, all right? We're going to assume that the length of this L is much greater than RC, and therefore in the center here, the B field, and I'm going to show you this too, you're going to like this. If you want to know the direction of a B field with turns, take your right hand, have the fingers on your right hand point in the direction of the current, and your thumb points in the direction of the B field or the flux. So the B field is in this direction, therefore the magnetic flux is in that direction. Can you all see it? Now, that's the B field. And the B field, it's just like if we have an infinitely long one. B field is going to be proportional to mu, proportional to n, right? Then it's proportional to I, inversely proportional to the area. I'm just going to say the area is pi RC squared. So that's the B field. Agreed? I mean L, pardon me. Not area, L. Sorry. Yeah, I put L. It's mu N I over L is the B field, and that's Webers per meter squared. Next, I calculate the magnetic flux penetrating one turn. This is just one turn. And I can even approximate this as just the B field times the area, or y'all with me on this, because I'm assuming that B field doesn't change in magnitude anywhere around here. It's the same. You'll follow me? So that's going to be equal to mu I, or mu Ni, over L, times the area. And I'm going to leave it as just area here. Now that's any turn. Now, this is the thing about my assumption. Because I made mu much, much greater than mu naught, I'm saying all the flux is going to flow within this tube here. And it's the same flux that flows here as flows here. And therefore, what I can say is, that is the flux through one turn. Now, if I'm looking for the mutual inductance between these, if I'm looking for the mutual inductance, Lm, is how much, what is the mutual inductance between this circuit and this circuit? Then I find the amount of flux that penetrates N2 turns, right? Are you with me? And this should be N1 here. That is the amount of flux that's penetrating any turn, right? Any one turn. But the amount of flux that penetrates this secondary circuit where I have N2 turns would be equal to, and this is the flux linkage, by the way, flux linkage. That would be equal to this times N2. I'm going to make it a point here. If this thing carried on, extended, and I had another set of turns here, and I had N3 turns here, and I wanted to know the mutual inductance between the first and the third, I would just multiply that by N3, not N2. Are you with me? But here it's just N2. That would be the flux linkage. And that would be between 1 and 2. And then the mutual inductance, L mutual between 1 and 2, would just be equal to the flux through 1 times N2 divided by I. So that means it's going to be mu N1, N2 times the area divided by L. And that's the mutual inductance between the first and second set of turns if they're wound about a toroid or about a solenoid. Either one, it won't matter. Because you can literally take this and just bend it around and make it a donut, and it would be the same thing. Y'all see this, class? All right, now the next thing I'm going to do is talk about magnetic circuits, and this will make the analysis a lot of this easier. And you've had your circuits, you've done circuits before with Dr. Irwin or somebody else, and so you know how to do this analysis. And what I do is draw parallels between magnetic circuit analysis and electrical circuit analysis with resistors and voltages and currents and such. So let me set this up for you. What we're going to be doing now is talk about things primarily related to iron core transformers, iron core bar magnets, iron core systems, things where the permeability is very large. And usually they do this. They're going to say, I'm going to start with a system where I just have some iron core and it looks like this, and you can all imagine this, yeah, I'm trying to draw this right, but so now I'm going to do this. I'm going to have N turns around here. Gross likes drawing this stuff. So I have N turns. And I'm gonna have something plus or minus voltage, but it creates a current I1 here. Follow me? Now if you look at that, the way I try to draw it, I'm trying to draw something where this is gonna have some mean height, h. This would be, let me do this one. The distance from here to here would be h. And I'm trying to make the distance from really here to here h as well. So if I remove that three-dimensional thing, and I just do this, if I put a box there, another box around it like this, and I just cut that like this and say that this is the area, cross-sectional area. And there's a permeability mu there, and these are my interns. Here's what we can do. Let me give you one other thing. Let's say the length here from the center points is going to be h, and the length from these center points, like from the centers right to here is going to be h as well. So I'm going to show you that this circuit right here can be analyzed by using the analogies I'm about to show you, where we take this circuit, this magnetic circuit, we can turn into electric circuits. And we can make the voltage in the electric circuit, that there's N turns and there's I flowing in this turn. So I flowing. We can take the voltage, by the way, voltage, let me put these up here. These are the similarities. This is electric, and this is magnetic. For electric circuits analysis, you had something called, it's an electromotive force. Motive force. At least if you had physics, you remember that. And the the EMF, if you will, EMF, is identified as a voltage V. That's the symbol. The electromotive force. If you think about it, the voltage motivates the flow of current. That's why it's called electromotive force. Well, the symbol over here is called motive force. And that's MMF. And that's in amp turns. It's amp turns, or AM, amp times T. It's usually, I think the symbol is AT, but it's amp turns, the number of amps times the number of turns. All right, and these two are exactly similar. So the voltage, which usually an EMF can be an MMF, and this is just N times I. Now, over here, for the electric, you had R and a resistance, and R was proportional for a constant cross-section material. It was proportional to the length of the material. It's inversely proportional to the sigma, the conductivity, and inversely proportional to the cross-sectional area. Do y'all remember that? This is resistance. And it's ohms, right? Well, here we have something called reluctance. And reluctance has the symbol script R. And reluctance is going to be L over mu A. So again, I'm talking about things with constant cross-section. If you have anything with a constant cross-section of a given length, so this would have cross-section A, length L, then you could say that the resistance here was equal to L over sigma A, or the reluctance would be equal to L over mu A. Either one. Got it, class? Now here, I want you to take a look at this. I've got this MMF, right? But what's the total length? Well, it would be 4H, wouldn't it? All the way around it. So now I'm going to put a reluctance here. And the symbol is the same as resistance, unfortunately. And that reluctance is going to be equal to, it's a script right here, L, or 4H. It's divided by the cross-sectional area, which is just A, and it's inversely proportional to mu. And actually, the units of reluctance, I don't even know. Actually, I know, but it would be amp turns per Weber, but there's another unit for it, but I don't even worry about that. Anyway, I'm going to tell you that's the reluctance, right? And that's like resistance. This is like voltage. Follow me, guys? So what would the current flow be? Well, the current, what we think of current in an electric circuit, I would be V over R, right? If it was an electric circuit. Here, it's not current, it's magnetic flux, and that's the other thing in parallel. So here we have current, it's in amps. Over here for magnetic circuits, we have flux, magnetic flux, and that's in Webers. So here the magnetic flux would be given as simply the voltage, or the MMF actually, the magnetomotive force. It's MMF over the reluctance, and that's really Ni over the reluctance. Do you all see what I'm doing here? Now that gives us the flux flowing. From there, I'm going to show you how we can parse this. If you wanted the B field, remember the flux here is in Webers, right? If you wanted the B field inside here, then we could say, well, the B field, we know is really going to be the total flux divided by the area, because the B field is in Webers per meter squared, right? You all follow me on this? Just think about this for a second. If we're talking about, if you had the current flowing in a system, right? And you wanted the value of J, the current density, you would take the total current and divide by the cross-sectional area, wouldn't you? Current density. If you know the total current, we're assuming it's uniformly distributed now. It's not, it doesn't, pile up on the edges. But if you just take the total current divided by A, that would give you J, the current density. If you wanted the B field, you take the total flux in Webers divided by the cross-sectional area. Now you have B in Webers per meter squared. All right? And by the way, that's just this divided by A, right? So you could say B field here would be equal to Ni divided by the reluctance. And you can put in all the values for reluctance, right there, the 4H over mu A. It's B divided by reluctance divided by A. So that would be the B field. Let me erase this. And the B field is in Webers per meter squared. Now, matter of fact, J would be the current density, and the parallel over here, J would be amps per meter squared, is B, and B is in Webers per meter squared. Now the next thing is E. You remember what E is? It's what? J, well, J per sigma. I'm trying to go from the one above it, right? Isn't current density divided by sigma equal to E? Sigma E is J, right? So divide J by sigma, that's the E field. And the E field is in volts per meter, right? Therefore, over here, for the magnetic side, if we take the B field and we divide it by mu, we get H. And that's in amps per meter. Here, it's in volts per meter, this is amps per meter. You all see this, guys? And these are the similarities. And this is for magnetic circuits. It's very easy to understand this if you take a look at it. Do you agree with me, class? All right, now, I started with a very easy problem to understand and trying to show you the parallels between magnetic circuits and electric circuits. And that's the way Dr. Wentworth's book does it. If you have Dr. Wentworth's book with you right now and you look, he's got a section on magnetic circuits, and then he has on electromagnets. I'm not gonna go to electromagnetics today, but I wanna go through one other thing. I could. The way to really learn this is do some problems, so. But one other thing, I didn't show you this yet, but this is really nice. Let's take a look at this problem. Let's assume I have the same situation. I have a bar here, it's got cross-sectional area A. It has a permeability of mu. Let's say it's got mean height dimensions h by h. And now I put n turns right there. And I ask you a question on a quiz Friday. And I ask you, what is the internal inductance of that system? Now, how would you get that? I want you to think about that. Well, think in terms of the parallel between that circuit and an electric circuit. For inductance, you always know you have to assume something. What do you assume? Current. So here I'm going to assume a current here. I have I. That means for the circuit, I would have a voltage here, or a pseudo voltage. It's actually an MMF of Ni, right? With me? Now I also have a reluctance, right? And that total reluctance is the reluctance of this whole system. I made them all the same cross-section. Usually in problems they have variable cross-sections, and I even have a little air gap there, but for now, let's just make it all one constant reluctance. So what is reluctance equal to? Do you remember we just did this? It's proportional to, yeah, and what would L be? 4H, right? Divided by mu, divided by the cross-sectional area A, correct? Now, the next thing would be like the current and electric circuit we got, but that would be the flux, magnetic flux in the magnetic circuit. And what is magnetic flux? If it's current, it's voltage over resistance. If it's flux, it's what? Ni or MMF over reluctance, right? So here the total flux is going to be Ni, right, over the reluctance, which is 4H over mu A. Are you with me, class? Now that's the flux flowing. Think about what we just talked about with inductance. That's the flux flowing through one turn, right? How much total flux flows through n turns? N times that. So if we multiply this by n, we get n squared, don't we? And that's the flux linkage. After we have the flux linkage, what do we do to find inductance? Divide by I. And lo and behold, if we divide by I, now we get the flux linkage. Oh, I'm sorry, we get the inductance. And that is the inductance. And see how easy that was? If we do it in terms of a magnetic circuit's equivalent, it's easy to do these problems. And you can do the toroid or the solenoid the same way. It's really easy. I want to tell you one thing. Usually with these problems, they do this. They'll put a little air gap here. Now, what that means is you're going to have one reluctance associated with this length, all right? That would be L over mu A. Then you would have another reluctance, but here typically mu here is mu naught if it's air. And that reluctance is usually the dominant one, because now it's, even though its L gap may be very small, this gap distance right here, L gap may be much, much less than the total length, but because it's mu naught, and typically mu in here is maybe 1,000 to 10,000 mu naught, typically this air gap is the thing that limits the flux that can actually flow. So you'd have to have a second resistance added or reluctance added in here for the gap. That's typical. I'll let you do some problems on this one. When we talk about, the last thing we're going to do is magnetic forces. Now,
I wanna just set the stage for this one, and then we get into chapter 5, and that's where it gets interesting in my opinion. When you think of magnetic forces or electromagnets, have you ever seen these junkyards where they have these cranes with large electromagnets on them, and they actually turn them on and they can pick up crunched cars and all that? Well, the way they do, we're going to study how those forces are created. And so the next class is important. Then we're going to jump into chapter 5. And chapter 5 is all about time varying magnetic fields and electric fields. And it's a really important chapter. I don't want to start it today, but I'm going to tell you, if I ask you to do a little bit of reading, would you please do it for me on Friday? Because I need you to at least be kind of prepped for this lecture. And it's going to have to do with EMF, electromagnetic forces, and it's going to also have to be created by, well, really, magneto-motive force, magnetic forces, and electric forces. But really, what I'm going to tell you is we're going to start with the full set of Maxwell's equations, not an abbreviated set that I'm using. And so it's a real important lecture, but I'm going to give you some reading and some homework. On Friday, for the quiz, it's the last, let's see, the homework on Monday, the material on Monday, today. So it's going to be on inductance or magnetic circuits or both, because you can get inductance from a magnetic circuit. Any other questions? Any questions at all? All right. I'm going to do my best to get here 10 minutes.